at all in SDN community. It's really our honor to have you here today. I think with that, we'll give it over to Ben. Thanks a lot, Ben.
Hi, happy to be here. Well, I think the first thing I want to point out here is you might be wondering about this picture. Somebody tweeted this photo on Twitter, obviously, and the tweet was in Italian, and some of the words on the slide are in Italian, so I don't really know what it means, but I think it looks cool. So I picked it up. I want to thank the organizers and Lightspeed for providing the food and drink. That's very nice. What I'm going to talk about today is really follows pretty closely with the title. I'm going to talk about the history of vSwitch, and then I'm going to move into some of the things that you can do with vSwitch today, and the part there that I'm most excited about is that I'm going to do a demo. It's not going to be a lot like many of the networking demos that I've seen before, where someone runs some commands and then says, "See, the ping works," and then they run a few more and say, "See, the ping stopped." I'm going to try to turn it into a little more of a tutorial for some of the advanced features of vSwitch that I think a lot of people tend to skip over. And after that, I'm going to talk about some of the things that we're working on now, and that you're likely to see in the future of vSwitch. To start with the past, well, if you don't know anything about vSwitch, then this probably isn't the talk for you, because I'm not going to describe what it is in a great amount of detail. This is the semi-official description from the website, and I call it semi-official because I can actually go and edit that website. But you can read that for yourself. But for me, the exciting parts are that you can effectively use vSwitch to write a program to control your network, to influence what happens to packets as they go through. A lot of people don't think of it as a program; they think of it as a flow table. But we've extended that flow table enough that you can actually. I believe it's Turing complete. I'll describe that in more detail later. But to me, that's exciting. The second part that's interesting is that it is fast, and it's not fast in every situation, but we're really working on that, and I'll talk about that in the future section of the talk. And third, we want it to be everywhere, and we're working on that. We're trying to port it to all the significant environments that we can. I know that a number of vendors have ported it to various switch platforms, and since vSwitch is open source, they don't even have to tell us about it, and they often don't. I only find out indirectly sometimes from people talking to me at trade shows. Maybe everywhere isn't a real word. That's the obligatory intro you have to give to explain to people what you're going to talk about. This is the part of the vSwitch history that I know the least about, because I was not actually involved. In 2006 and 2007, Nick McEwen's group at Stanford, and especially from my point of view, Martin Casado worked on a project called Ethane. And if you look at the description here, Ethane is not so far from OpenFlow in the concept. It wasn't quite as general purpose as OpenFlow, and the implementation wasn't as robust and mature as Open vSwitch, but the goals were closely related. So I knew a little bit about this because Martin, his office at Stanford was across the hall from mine, and so we'd go and eat lunch a lot at the cafeteria or the little restaurant in the basement of the Med Center, and he'd tell me about the exciting things about using policy languages to control who can access what on the network. I went and I looked at one of the Ethane papers a little bit yesterday when I was preparing for the talk, and actually I guess it was the research website. And what impressed me the most about it was the claim that you only needed to support a few thousand flows to run a large network. We found that this is not in fact true. Networks have a lot of flows. They may only have a few thousand active flows at any given moment, but there are definitely cases where this is not true, and you have to provision for and be prepared to handle the worst case. So I think there was some optimism about what you need to actually handle there that I no longer share. But that's the sort of thing that you can get away with in a research project because it's only other academics who can argue with you, and you don't actually have to prove it in a commercial environment. So let's see. I started working at Nicira when it was founded. As I was graduating, I talked to a bunch of startups. Some of them did well. Some of them had small exits. Some of them are still startups, kind of strangely enough, even 5.5 years later. Martin impressed me the most with the goals. The idea was from the beginning, change the world of networking. So I joined, and the initial name for what became Open vSwitch was Vigil or Vigilante, and that is because the name Nicira comes from Sanskrit, and it means vigilant. And so I naturally took this and had to make it more extreme, and Vigilante seemed like the right name to me. So Martin made the first commit, and over the next month or so, we did a lot of work on it. The most bizarre thing I found when I was looking through this old repo is that we very quickly converted the whole code base to C++. I have a funny relationship with C++. It's got this huge language standard. It's something like 700 pages long. And I went and I read the whole thing at one point. And it's really complicated. It's got whole pages that are paragraphs that explain one very specific ambiguity you can find in the grammar for it, and then at the end of the paragraph say which way you're supposed to interpret that. And I actually at one point went through all the books I have on C++ and tried to compose sort of some notes that referred back to all the advice. And when I got to 60 pages of notes, I decided that maybe it wasn't language for me. But at any rate, that didn't persist into what you see in Open vSwitch today, thankfully. Otherwise, I'd have to go study the language standard to make any actual changes to it. So we very quickly hired a couple of other people, and I just wanted to call out two of the ones who did some really amazing things. Natasha Good, who we hired right out of Stanford as an undergrad. She did some amazing things in this Stanford networking course, and it's always hard to figure out who you should hire straight out of undergrad, but She's done just amazing things. And Justin Pettit, who I also knew slightly from Stanford, and Martine knew better. Actually, I want to tell a story about my interview for Nicira. So after Martine convinced me that I should consider them, I had to interview with Scott Shanker, who's a networking professor out of Berkeley, and one of Nicira's founders. And he was using Nick McEwen's office in the Stanford CS building that afternoon. And I walked in and sat down and said hi, and he said, "Martine tells me you walk on water. Is that true?" And in my memory, it was like a growl, but Scott doesn't growl, so I must have just, that's just the way I remember it. The interview picked up a little from there. We were developing fast. When I go back and look, I'm amazed the amount of stuff you see in individual commits for a day. And I just want to call out a couple of them here. We weren't planning to make this repository public, so there's probably more swearing in the commit log than we do today. Add crap needed by crappy UML crap, which refers to user mode Linux. By the way, we've never done anything with the UML modeling language. I don't even know how to do that. So our goal from the beginning wasn't to just create a switch. The goal was to create an entire, what we call today an SDN environment, although nobody had invented the term back then. And so the first source tree had both a skeleton for a controller in it, as well as the skeleton for a switch, and they actually shared quite a bit of code at one point. Later on, of course, they got separated. The controller in there became nonce, which stayed in C++, and the switch got turned over more or less to me to handle for a while, and I converted it right back to C++ because back to C because I couldn't stand C++. So after we'd done Vigilante for a while, Nick started talking about founding a sort of a consortium at Stanford, which became known as the OpenFlow consortium. And this was partly, as I remember it anyway, a political move because we figured that no one was going to listen to like 3 or 4 guys working out of what looked and smelled like a dentist's office on California Avenue in Palo Alto. But they might listen to a consortium run out of Stanford. And so at this point we did a search and replace on our code repository, replacing Vigil by OpenFlow, I guess, although we had some other names there that we considered. And we also replaced the Nicira.com email addresses by our Stanford email addresses because we wanted to really run under the radar with regards to the industry. So you can see the dates there that sort of add up to that. And by the beginning of 2008, and if you look on archive.org for the Nicira website, you can probably find our original website that said something like, look for big things coming spring 2008. And of course, we didn't ever actually announce anything until like 2011. So that website was a little embarrassing after a while. So after we did that, we started a new repository with much of the same code in it, but with the Nicira origin sort of scraped off because of what I said. And you can see the descendants of that repo still on the old vestigial website of the OpenFlow consortium, which later more or less replaced by ONF, but the website's still there. So we continued doing some development together with the OpenFlow folks at Stanford, who were mostly next grad students, and they for a while they were merging our changes, but eventually, I don't know, maybe they got tired of the pace we were developing at or something like that, but they stopped merging, and so that from our point of view, that was the end of the public bits of the OpenFlow reference implementation, as it was called. So in 2008 at Nicira, we came across this idea of let's do something with virtualization. And it seems kind of obvious at the time, but when Nicira started, the focus on virtualization didn't seem that obvious. And I'm no business or strategy kind of person, so I can't tell you how it came up. But by the middle of 2008, we figured out that it would be a good idea if we could get our stuff to run on virtualization platforms. And the first target that we had was Citrix Xen Server. And we spent a lot of the time picking Xen Server apart. I remember disassembling binaries and things like that, at least enough to figure out that they were using Objective Camel as their main programming language, and that if I wanted to intercept certain things, I was going to have to actually binary patch them. Fortunately, it didn't come to that. I was prepared to do it because I'd done it before at Stanford. The startup Mocha 5, some of you might have heard of them. For a long time, they were actually paying me royalties on the binary patch that they were using for modifying VMware Workstation to do what they wanted. So we figured out that we needed various virtual switch features, and at the beginning of December, we had, on the one hand, a feature list, and we had more or less agreement from Citrix that they'd look at it at least, as long as it was done by January 1st. So at this point, we had no code. So I spent a solid week in the office writing definitions, hiding out in Scott's office, trying to avoid all email and human contact. Let's see. For a long time, vSwitch had this feature called the bridge compatibility, and what this meant was that if you were using the Linux bridge and your software stack required that, then you could instead of loading that Linux bridge module, you could load the vSwitch bridge compatibility module instead. And then this would intercept all the system calls, all the functionality that normally talks to the Linux bridge, and modify it so that it instead talked to vSwitch. And the sole reason that we wrote this whole thing was so that we could get ourselves into Xen Server for experimentation reasons, without having to have Citrix's cooperation, because the Xen Server binaries, which were proprietary at the time, though now they've become open source, the Xen Server binaries made all these direct calls into the Linux kernel to manipulate bridges, and so we had to intercept all this stuff at this very low level to fit ourselves in, and we spent a long time writing and then improving this support, and later, when we were actually working with Citrix, I found out later that that I'd spent something like a solid week trying to finish up some tiny minor point in the bridge compatibility, and the only thing in XenServer that required this, as it turned out, was some script their QA ran, which they could have rewritten in like 3 minutes. So I felt like I'd wasted a lot of time at that point. We had a January 1st deadline, like I said, so I spent, it basically ruined my Christmas. I spent my whole Christmas just banging away at this code and managed to get it feature complete on January 2nd, which we figured was probably okay, that they didn't really need it on January 1st, did they? Here's another point, a bit of historical interest. I found that January 8th, 2009 was the last commit that Martin made to the whole code base. After that, I guess he really transitioned to spending all of his time on the road talking to potential customers and plotting strategy and so on, which it turns out that he's really amazingly good at. Good programmer and business guy. We managed to get Citrix to take a look at this, and then after I'd spent all this time, I realized I found out in a meeting that I totally misunderstood how our controller software was planning to use this thing. And so I had to spend another week or so just rewriting the whole thing so that it would work with what we wanted our controller to do. So the controller that we were working on at the time turned into, I think it's actually a Citrix branded product, the Citrix Distributed Virtual Switch DVS. But that's all Nicira code, and I believe that Nicira still maintains it for Citrix and the customers. In March, I went on my first and only business trip for Nicira. It was the craziest trip I've ever taken in the sense that we were in Cambridge, England for something like 36 hours. We hopped off a plane. We were in 2 days of meetings, and then we hopped back on a plane. I was so crazy jet lagged that I think Justin must have saved my life a couple of times, just keeping me from walking in front of buses and things that were coming from the opposite direction of what I expected. He still jokes about that sometimes. So this was vSwitch-D, but the name OpenVSwitch hadn't been invented yet. So OpenVSwitch came along in 2009 and the whole idea behind OpenVSwitch was that the Nicira controllers would be a lot more valuable if they could run, if they could control more software and hardware. If we keep it proprietary, then you can only run it where we can compile it and where we choose to port it. But if we make it public and open source, then in addition to being useful to people for other reasons, it's useful to us. OpenVSwitch everywhere became a goal at that point, and so we started another repository, the OpenVSwitch repository, starting from the code that we'd written for vSwitch-D, and we created some mailing lists. And here's a point that I think a lot of people don't appreciate. We get a lot of flack sometimes for not supporting OFConfig, which is the official OpenFlow configuration protocol. You can use it to create and destroy switches. You can use it to configure them, and so on. Basically, it's parallel to what an OpenVSwitch you do with the database. But in fact, we had good reason that, for using our own protocol, which is that we designed, implemented, and checked in our database configuration a full 2 years before the OF-config working group even had an outline of their protocol. And in fact, the OVSDB specification is currently reviewed to be an informational RFC. So I think that'll give it another sheen of legitimacy. It felt a little bit at one point like OF-config was trying to steal our thunder when, I mean, the way we view them, they're just the Johnny-come-latelys to the game. So OpenFlow 1.0 came along in 2010, or I guess it could have been late 2009, and we soon added support for it. And since then, since that time, for the last 3+ years, we've done our best, and I think we've done a pretty good job of making sure that every Open vSwitch version is wire compatible and mostly anyway database schema compatible with previous versions. And then in May we released Open vSwitch 1.0, and we were really surprised at the time. It seemed like it got a lot of press and a lot of attention. The part that surprised us is that really it was just a matter of putting just labeling it as 1.0. The quality and the implementation had been about the same for some time. It had really stabilized at that point. That's one of the reasons that we that we decided to start making releases more frequently a little later, because it turns out that these numbers are actually important to people. If you tell people that your master branch is stable and they should feel free to use it for production, even if it's true, they are really reluctant to do it. But if you label it as 1.0 or 1.3 or whatever, it makes them happy. And so for me, that's the most interesting part of the history of Open vSwitch. Of course, in July of last year, the acquisition of Nicira by VMware was announced, and I can tell you there was a lot of partying. For me, it was a real release of pressure, because I had found out about the acquisition a couple of weeks before. Martina told me, and I'd been in all these meetings over at VMware, and I wasn't allowed to tell anybody, and not even my wife, because if it got out, it could. Don't ask me why. I don't understand business. If anybody found out, then it could scuttle the deal somehow, and so. I basically had to lie to all my coworkers. What are you doing? Why are you taking personal days in the middle of the week when you never do that sort of thing? So the party was pretty amazing. We had just a fleet of taxis appear at the Nicira headquarters and take us all to Antonio's Nut House in Palo Alto, which is not a nice place, but it was the place to go, because our first office had been right across the street from it, and so we had a lot of good memories there. So that's my summary of the history of Open vSwitch. So if you want to look at what we've got now, I went through our repo, our public and the previous repo last night, and took a look at the email addresses of contributors, and so these are some of the places that have contributed patches, not just sending bug reports, but actually authored patches. And I'm sure there are other organizations that I left off, and I'm sure there are other ones where they posted from their Gmail account or something like that instead of the official one. So to me, this reads like a good cross section of the industry. So here's the what I call the Hall of Fame. It's the list of all the people who've authored at least 10 commits, along with the number of them that they've authored. I know that at least Kyle Mestry is here. I don't know whether any of our other Hall of Fame members are here today. But if you're here and you haven't met me, please come up and say something to me afterward. So this is sort of a summary of some of the things that I feel like I've really learned from vSwitch development over the years. So when we started Nicira, it was really clear that efficient packet classification was going to be very important. And by packet classification, I mean that if you've got a packet and you've got an OpenFlow flow table, then what's the best match in the OpenFlow flow table? Now, OpenFlow flow tables are not simple from many points of view. You can't just throw them in a hash table because all of them might have different sets of wildcards. You also probably can't afford to take the rules from highest priority to lowest and just check each one, because if you have 1 million rules, then you may have to you'll have to do 1 million checks if, for example, the packet doesn't match any of them, and so it turned out that lots of people had considered this problem. So my strategy when I'm faced with a difficult problem in computer science is usually to find all the papers I can and read them, and usually you'll find that the first round of papers you're looking at doesn't help. So you look at the references, and you find yourself chasing stuff through the ACM archives and the IEEE journals for a long time. So I did this, and I wasn't happy with any of it. A lot of it was hardware oriented, and the ones that weren't were often very, very complicated, so that if you had 1,000 rules or 1 million rules, you would have to spend just seconds or even minutes of CPU time processing all these rules before you'd be able to make your first decision. And then when something changed in your flow table, you'd have to do it all that pre-computation over again. And in the meantime, what are you going to do with all the packets that are coming? You're not in good shape. So Open vSwitch has gone through a few different flow classifiers, and you won't find any of them in papers. And I think that for our purposes, they're superior to anything I could find in the literature. I keep meaning to try to actually write a paper on this stuff with actual benchmarks and so on, but until recently anyhow, writing papers has been pretty discouraged just on the basis of we got to get the damn product out. I encourage you, if you're looking for a good packet classifier, go look at our source code. It's in there, it's documented. So my second point here is that we've gone through any number of implementations of code. I've rewritten important parts of our code any number of times, and it gets frustrating sometimes. But every time you rewrite it, it gets better. And I think the low point there was probably when we were working on trying to submit the Open vSwitch kernel module to upstream Linux for the first time, and we got back some really negative comments from some of the reviewers on the networking mailing list. So this is just my way of saying that you got to be prepared to do it again. I am prepared. Hey.
How big is N?
How big is N? Ooh. I think it must be at least 4 by now, in terms of just what I'm talking about there, the kernel module. And not every line of code is changed every time, but the overall design has. And we may have another rewrite coming up. I'll talk about that at the end. So another lesson that I learned is that we really threw stuff together to get something working at first. And then we turned it all over to this OpenFlow consortium at Stanford. And I had figured the whole time that when it got to people who were writing standards, they'd fix all the obvious mistakes that I made. But they didn't. They didn't even notice them. They spent all their time arguing over essentially, what color should it be. That I found it really frustrating. And if I do something like this again, I'll make an attempt to do the things that bugged me about that right from the start. Another thing is, from the beginning, we had this idea that you could afford to send the first packet of every flow to a controller across the network. This is really seductive because when you've got the first packet of a flow on your controller, then you can write really straightforward logic to figure out what should happen to it. But despite all the claims we made, it just doesn't scale. You can't afford to send the first packet of every flow over your network. For one thing, if the network's down, then you're in big trouble. And for another, the bandwidth and the latency just isn't acceptable. So all of the controllers that Nicira has released do not do this sort of reactive programming. They set up all the flows in advance. In-band control is really hard. And by in-band control, I mean the sort of situation where you've got a network that you want to control with OpenFlow, and you want to control it with a OpenFlow controller that is on this network that it's controlling. We spent countless days and weeks trying to get this right, and we eventually got it to the point where it is now, where it works, but we're afraid to ever change anything. And so if you propose a change to it, we're going to be really suspicious. And please don't think that we're jerks. We're just, that's the history. And finally, performance is a big thing. People won't use your software for networking if it isn't fast enough. But I've been surprised so many times about where the performance bottlenecks really are. And the hardest part of figuring out where the bottlenecks are in networking, I think, is finding out what are people's actual use cases. And people don't even necessarily know. You can't go to some customer and say, okay, what's your traffic look like? They've got no idea. And maybe if they do, the sorts of answers that they have probably aren't the ones that you need. And only now are we finally getting to the point where we can use actual traffic patterns that our customers have to really optimize our software for real traffic. The sorts of guesses that we made and synthetic patterns just don't cut it in the end. So here's the part that I'm excited about. This is where I'm going to do a demo. And like I promised, I'm going to. There we go. Okay. So the demo I'm going to do is based on this theme that we made kind of a mistake in OpenFlow and in vSwitch. OpenFlow has this action called normal. And this was Nick McEwen's idea. And the idea behind normal is that you have some expensive switch that you're sticking OpenFlow on, and this expensive switch has some sort of a switching pipeline, and OpenFlow might want to be able to take advantage of that. So if you set up a flow and you tell it use the normal action, then the switch is supposed to take the data for that flow and just do whatever a switch should do. Things like VLANs and mirroring and MAC learning and that sort of thing. So this is all well and good, and his intentions were good. I think the mistake was that in Open vSwitch, we actually implemented this to do what a switch was, to do what one of these switches would do. And the mistake there is that it really reduces the pressure to make sure that you can do similar things with OpenFlow. And you want to be able to do similar things with OpenFlow because that's the only way to make these things flexible and extensible. If you can't wedge something into the middle of one of these stages, one of these pipeline stages that a switch is going to go through, then you've really just you've got an inflexible system again, and you haven't really won anything. And for a long time, we didn't have any pressure to do this, and so Open vSwitch lacked features that you could use to implement a normal switching pipeline unless you use normal. So, what I'm going to demonstrate is how you can use features of Open vSwitch without using normal to do many of these things that you would in a switch's normal pipeline. I'm giving sort of a simplified example, but I think it demonstrates the principles. So I'm going to demonstrate how to write a Open vSwitch flow table for a switch with these pipeline stages. So each of these stages is going to correspond to one OpenFlow flow table, and packets will proceed from table 0 to table 4, and at that point they'll exit the system and go to where they should with the proper VLANs based on with MAC learning that happens in the middle. So the stages that I'm going to go through are a simplified form of admission control, where we discard packets that are clearly invalid. In the second stage, we'll do VLAN processing of the inputs. So, for example, we'll make sure that that packets that arrive on access ports do not have a VLAN header on them, and then we'll attribute them to that to the VLAN for the access port. In in stage 2, the third OpenFlow table, we'll show how you can implement MAC learning in Open vSwitch. In table 3, then we'll look up the destination for the packet on the basis of where the packet's destination has been learned, presumably on previous packets. And then in the fourth stage, we'll actually output the packet to the correct ports on the correct VLANs. So the features that I'm going to go over that are, to my knowledge, unique to Open vSwitch, these are OpenFlow extensions, are listed here. The most important one of them is what we call the resubmit action. And what resubmit does is it causes whatever packet you have in your system at the current time to be looked up in some other OpenFlow table, and then it executes whatever it finds there. And then afterward, it returns to where you started. So it's a little like a subroutine call for OpenFlow. So the original motivation for resubmit was to avoid what you can think of as the Cartesian product problem. So if you've got one set of criteria based on, say, one field for what to do with your packets, and then you've got another set of criteria based on some other field to decide to do with your packet, then if you only have one table, then you have to write potentially n times m rules if you've got n criteria on the first and m criteria on the second, and so if you've got a third set of criteria, then you have to multiply by that, and so on. So your flow tables get very big and unmanageable very fast. But if you can do one lookup here and then one lookup there, then you save a lot of space, and it's a lot faster. The second action is one that we added more recently, and it's called learn. And it's called learn because our main goal for this is to implement Mac learning, and so it's supposed to be suggestive. But in fact, you can use learn to insert arbitrary rules in any OpenFlow table based on the contents of the packet that you're currently processing. So you can use it to, besides Mac learning, you can use it to do things like, if you've got an outgoing flow and you want to open up a hole in your firewall for the return flow, you can do that easily with learn. And there are other things that you can implement with it. Registers. So OpenFlow has all these packet fields that it can look at. Registers are just additional data that your flow table can manipulate as it goes through, and then match on it later to do something else. And if you only get one thing out of this, then I'd like you to learn about the oath proto trace command. And what this does is it's an open vSwitch command. You run it, and you provide it with information about a flow. And then it shows you step by step what would happen to that flow as it goes through the set of OpenFlow tables. It's the number one debugging tool that we use for flow tables at Nicira. So the test case that I'm going to look at for this demo is we're going to suppose you have a switch with 4 ports. One of them is a trunk port. I'm going to call it P1 and put it on OpenFlow port 1. And then 3 access ports, P2 on port 2 with as an access port for VLAN 20, and then 2 ports that are access ports for VLAN 30, and let's call those ports P3 and P4, and put them on OpenFlow ports 3 and 4. So this is something that it's valuable to be able to refer to. So I'm going to go and draw the same thing quickly over on our whiteboard here. So now I'm going to flip out of the presentation and actually show you some Open vSwitch stuff that I set up last night. So what I'm going to do here is start up a little script. So what this script does, well, it helps if I run it with the right argument, doesn't it? There we go. So what this script does is it starts an Open vSwitch in what we call dummy mode. And in dummy mode, it doesn't actually talk to any hardware in your system. So you don't need to have root privileges, you don't have to have the kernel module, etc. On the other hand, you can still add ports to it, and you can run commands that cause packets to be received. You can manipulate flow tables, and so on. And so what I'm going to do is run a program that can you guys read this fairly well, or should I make the font bigger? No. Okay. Okay, so what this does is it creates a bridge, makes a dummy bridge, then it adds a bunch of interfaces and brings them up. And these are the interfaces that I've drawn over here on the board. Now what it doesn't do is it doesn't set up any of these features. It doesn't configure things as trunk ports or access ports or whatever, because we're not actually going to go through that. We're going to implement all of this in the OpenFlow flow table. So what I'm going to show you first is how we can set up the stage 0. And like I said before, the stage 0 is to do some admission control, drop some packets that are clearly invalid. Now there's all kinds of validations that you can do, and you could write those as additional flows. But all I chose to do was a few really basic ones. So you can see them there, and I'm not going to go through every flow that I'm going to add in great detail, but maybe if I explain a few of these, you'll be able to figure out the rest, or at least get a place to start. So what this is saying, OFKittle is a OBS program that lets you control a switch. So it's adding a flow to our switch VR0. It's going to add it into the OpenFlow table number 0, which is where all packets come into the OpenFlow switch. So this is where they get looked up first. And it's matching on Ethernet packets with an Ethernet destination. It's one of the reserved multicast protocols. So that's protocols like STP, LLDP, the sorts of things that a switch is not supposed to pass through. And then we're saying that the action for that should be to drop it. And we have another one here that matches packets with the multicast source, which doesn't make sense, and drops those. And then anything else that doesn't match one of those rules, we're telling it that we want to run this resubmit action. And I was telling you about that before. So this just says, okay, now take our packet that passed through and look it up in table 1. Okay, so what I want to do now is show you what we can do to see whether this works. So here's some old proto trace commands, and let me explain what these do. So this says.
Can you scroll out a bit, because it's kind of difficult for us to see it in the bottom. Just do a clear.
Oh, it's too far down?
Yeah.
How's that? Okay, great. So let's look at this first command here. So this is saying, tell us what's going to happen if a packet comes in on port 1, that is on our trunk port P1, and it has, oh, I'm sorry. These are the tests for stage 1, and we're still on stage 0. Okay, so a packet comes in on some port, and it's got one of these reserved multicast destinations. So that should get dropped. So let's see what happens when we actually run that. So it's saying that it looked it up in the table. It found a rule, the rule that we added that matches on these reserved multicast destinations. And the OpenFlow action there was to drop it. And so in the end, the packet got dropped. So here's another case that's slightly different. It's almost one of those reserved multicast, but it doesn't actually match. So let's see what happens this time. So what happened this time is that it matched our final rule that anything that doesn't match those drop rules gets to. And so its action was resubmit to table 1. Now we haven't this here tells us what would happen. What happened to table 1? We haven't added any rules to table 1 yet, so nothing happened. But it would get looked up there. It did get looked up there. So let's implement our stage 1. And if you remember, stage 1 was to do our input VLAN processing. In other words, figure out for the trunk port, anything is okay. Whether it has a VLAN tag or not. So what we do there is we came in on port 1, we resubmit to table 2. And you don't have to write any of this stuff down. I'll make this all available on my website, no problem. So, so if it comes in on the trunk port, we just send it on to the next stage. If it came in on any of the any of the access ports, then we match. If they did not have VLAN headers on them, then we attach the correct VLAN tag for that port to the packet. So after this stage, a packet has the VLAN tag attached to it for whatever it should, regardless of whether that was what it came in with. So for port 2, we attach VLAN 20. For port 3 and port 4, we attach VLAN 30. If it didn't match any of these, then we drop it. And so this makes sure that if a packet comes in and it does have a VLAN tag attached to it, but it's an access port, then it gets dropped. But you don't have to believe it from the rules. We can actually run some tests and try this out. So if a packet comes in, what is that? If a packet comes in and it has a VLAN tag attached to it on our trunk port, then it should continue to stage 2. And in fact, we can see that it got resubmitted to stage 2 after it got resubmitted to stage 1. Now, on the other end, something like that should happen if we, here's what happens if there's an untagged packet that comes in on P1. It gets tagged with VLAN 20 and resubmitted to stage 2. And here, in fact, in stage 2, you can see that it had VLAN tag 20 attached to it. Previously, it did not have a VLAN tag attached to it. You can see that from this here. So that's working properly. And then the last thing that's worth trying is if we do have something with a VLAN tag on it, it comes in on an access port, does it get dropped? And we can see, yeah, it gets dropped, it doesn't get resubmitted. So let's run our stage 2 here. This is where the learn action comes into the mix. This is where we do our Mac learning. So this deserves some explanation. So what this table is saying is that we take our packet and we use it to set up another flow in OpenFlow table 10. And OpenFlow table 10 is going to be our Mac learning table in our switch. So it's a little, well, it's actually really hard to read, but what this is doing is it's setting up flows in table 10 that match the same VLAN the packet came in on, and do a destination match for the Ethernet source address that the packet came in on. And then finally, that's the match. So that matches our Mac learning entry. And then the action that occurs when that matches is that we stick the input port that our packet here came in on into a particular register, the low 16 bits of that register. And this action here doesn't actually it doesn't actually run that rule. It just modifies the OpenFlow flow table. And our final step here is to resubmit to table 3 to go on to the next stage. So this one is kind of interesting to test. What we can do.
So you said this went through table 10, and then you resubmitted back to table 2.
It modifies table 10, and then it resubmits to table 3. We haven't actually used table 10, we've only modified it at this point.
And which table is it that took this action?
This action is in table 2. So this is our Mac learning stage. So what we can see here is this command will put a packet in on our trunk port on VLAN 20 with this source MAC address. And this is new. What this means is that don't just tell us what's going to happen, actually do it. Actually run that packet through the switch. So if we do that, then we just did a learning. We just did Mac learning. So what we can do now is look at our table 10 and see what rule got created in table 10. Okay, so here's our rule that we just created, and the interesting part is exactly as we'd expect. We put the packet in with a VLAN 20. We can see that that this rule is matching on VLAN 20, although it's expressed as hex 14. And we can see that it matches on the destination address, dest, that's the same as the source address we sent the packet in on. And that when that happens, when that matches, it loads the input port, and we sent this in on port 1, our trunk port. It loads that input port into our register 0. So we can use that in our next stage for learning. And let's see here. Here's a couple more that we could do for learning. I think I'll skip over those since it looks like we're short on time. I'll just get through our example here, and then if we're short on time, we can wrap up. Okay, so here's our stage 3 that actually does the map learning, or that takes advantage of the map learning table. So this takes 2 rules. So we have a high priority rule that matches any multicast or broadcast packet, and it skips the lookup in the MAC learning table because if you have multicast or broadcast, you should send it to all the ports. So it just goes on to our next stage. And otherwise, we resubmit to table 10, which is where we have our MAC learning rules, and that will load our output port into the register, and then we go on to the next stage. I think I'll skip over the test of that. Like I said, I'll make this available so you can verify that it works. And here's our final stage where we actually execute, where we actually send it out based on what we learned. So what we're doing here is we're matching based on the learned destination, and then we're sending it out to the proper port. So if our destination is the trunk port, then we send it out with whatever VLAN's already on it. If it's one of the access ports, then we have to strip off the VLAN tag first before we send it out. Now, if we haven't learned anything, or it's multicast or broadcast, in which case red 0 is 0, then we need to send it out on all of the ports, and all the ports that have that VLAN. So we need to do different things depending on whether it's the VLAN supported by one of our access ports or not. And let's see if I wrote some good tests for this. I think I did. Okay, so here's an example. If a packet comes in on a trunk port and we're supposed to send it, and we're supposed to broadcast it, well, actually let's do it for this one because it's more interesting. It came in on VLAN 30, so this should get output to our ports P3 and P4. And as you can see, the final actions that it comes out with, if you read through this, is that it pops off the VLAN tag and outputs it to ports 3 and 4. And let's try one where we actually do some learning. So here, first, let's learn this particular MAC address on access port P3. And you could read through that if you wanted. And then let's send a packet in on our trunk port tagged for that VLAN with that as the destination. And as you can see, it sends it just to port P3 with that VLAN tag stripped off. So that's my that's my demo. So this is the stuff that I think is fairly predictable and is going to happen, but I don't really think it's worth talking about much. All this stuff's going to get implemented. Contribute if you want it to happen faster. So what really is a problem, and always has been a problem, and even if we do a perfect job, people will still want it to be faster, is performance. So because of the, and here I'm only talking about our software switch. Our Open vSwitch will run on will run on all kinds of hardware in addition. But this is the software switch. So there are some situations that are not a problem. If you have a small number of long flows, if you have a dozen flows, and each of them are a gigabit, we can handle that. That's easy because each of those flows just occupies one little cache entry in your kernel. Packet comes in, hash it, bang, send it out to where it's going. And if you tweak it a little bit, you increase your number of flows, but they're still fairly long. That's not really a problem either for the same reason, because caches handle that really well. And in fact, one of our weaknesses is just that we don't have great heuristics right now for figuring out exactly what we should keep in the cache. But we're tuning that, and like I said, we're finally starting to get some real customer data on what's really important to people, and so that's going to get better. I'm not worried about that. The real problem that's hard to solve is when you have a large number of flows that are very short. If you have, for example, someone running HPing at 1 million packets per second, and in extremis, this is something that you can't expect to handle in any way, because say you've got a 10 gigabit NIC. You can receive some absurdly large number of packets over that in a given second. People are firing them at you as fast as possible. So in extremis, you can't handle that. And you put 10 gigabit NICs in your system, the thing will melt, and it's not a thing you can do about it. But it's the cases in the middle where it's not easily cached, and it's not so many that you can't expect to even look at the packets at all that are a problem. So there are various ways that we can address these middle cases. We use patch ports a fair bit at Nicira. Most of you probably don't, but we made them faster. I've got a technique I'm working on called batching, where when a whole bunch of packets come in at once and they look more or less similar, except say for the TCP ephemeral port, then we can handle them together, and we save the time that we'd otherwise spend looking them all up in our flow tables. A final technique that might help is threading vSwitch. Currently, the vSwitch is one process with one thread, and if packets are coming in fast, then presumably we could handle them faster if we could use all 8 cores. Now that, I have a question mark there, because that'll work if you're building a dedicated appliance that's just supposed to forward packets. But if you're on a hypervisor, and that's the case we're most worried about, you don't really want to spend all 8 cores processing packets, because there's presumably someone in your VM who actually wants to spend some time, like doing something with those packets. There's a couple of obvious techniques that we don't think are likely to help, and we've definitely looked at them, and people keep asking about them. One is when a packet comes in and the kernel module doesn't know what to do with it, it sends the packet to user space. And the question that people ask very reasonably is, what if the kernel kept that packet, and so when you knew what to do with it, it just sent it off, and you didn't have to copy it back into the kernel? And we've tested this. It generally doesn't make a difference because the packets that come to user space are generally the first packet in a flow. And the first packet in a flow is usually something like a TCP SYN that's just a few bytes long. And so the bytes that you don't copy, there just aren't very many. So you don't save very much time doing that. People also suggest that speeding up the interface between the user and the kernel would help. Maybe, but when we run profiles, there's that interface is not soaking up a lot of CPU time. When we do a profile these days, it's very flat. There's no real big spikes in it. About the highest use of CPU is like 2% or something like that in terms of hotspots. And if there were obvious spikes, we hammer them down.
How about mid-time?
Wait, we'll get to that. So here's another aspect of performance. One thing that makes performance seem slightly less important is if you're fair. So if you're running a cloud and there's just one VM on a given hypervisor that's soaking up all the traffic, and they manage to starve out all the other VMs so that they can't get their traffic out at all, then that looks really bad, and that makes people mad at you. But if everybody can still get their traffic out, then it's much less of a problem. So we've done some work on this. We now have a pretty good story on making sure that each port gets equal access to the switch. But the problem with that is that most of your traffic goes through only one port, or comes in on only one port, and that's the port that connects you to your upstream switch. And so the next step is to try to get some more granular per tenant or per destination kind of fairness, and so we're working on that. So as for actual solutions beyond fairness, we're kind of thinking about two different approaches right now. One of those is these various techniques that you can use to get every packet that comes in on a NIC to user space in a much faster way than you can with the standard techniques. And there's a bunch of these. There's the one that's come up recently is the Intel Data Path Development Kit, the DPDK. But there's a couple of older technologies out there. One's called PF Ring. One's called NetMap. So this is really seductive because if you can get every packet to user space fast, and that means that you've got what I think of as ultimate flexibility. You don't have to be limited by what your kernel module can do. You're only limited by what you can do in user space. And user space is so much easier to upgrade and to modify and to hack on, and you're not going to blow up your system if you screw it up, and so on. This is really seductive. The downside of this is that all of these, to my knowledge, require you to not just compile and install a kernel module, which we're already pretty good at since we have a Linux Open vSwitch module, but they require you to modify all of your NIC drivers as well. And if you're working with commercial customers, they're not really hot on that because they could lose the support of whoever they get their operating system from. Red Hat's probably not going to be thrilled with it if you just start randomly modifying your kernel and then asking them for support. So this will work well if you control the whole system, but not if you're just trying to help someone out on their system that they already like. So the other approach that we're looking at is what I'm starting to call mega flows. So the term flow is really overloaded. in this area. And so I've started using the term microflow for something that's exact match, that matches precisely, for example, 1/2 of a TCP connection, and a megaflow for something that's more like OpenFlow, where you can modify, or where you can wildcard some fields, and bitwise match in others, and maybe even do a range match on some. To date, our kernel module has only supported microflows, but if we could say ignore the ephemeral port, or in some cases just match an L2, then we could do a lot of stuff without having to call out to user space at all, and that would speed things way up. I think that the every packet user space approach is more elegant, but we can do megaflows without having to change out the NIC drivers, so it seems more practical. We can also implement megaflows, or fairness using megaflows, but I won't go into that. It's actually interesting. One of the early versions of the OpenFlow reference implementation had megaflows. We didn't call them that, and they weren't efficiently implemented because we didn't have a decent flow classifier at the time. But it's an idea whose time has come again, I think. So here's some of the people who've been involved in one way or another, and I want to say thank you. And now I went over by 15 minutes, sorry. And I'm happy to take any questions.
So in the example you gave, you go to a fork state, right? In a real-world implementation or deployment, like say how many state typically the packet will host?
So the question is, how many stages are there in a commercial switch?
Right.
I've never worked on a commercial switch. I worked this example up in about an hour, based on my knowledge of how switches work. The NVP controller uses something like 30 or 50, or up to 50 stages, I think, when in its OpenFlow flow table, or its vSwitch flow table. But it does some pretty sophisticated things. Yes?
If I correctly understand...
Can you speak up?
If I correctly understand, you need to push state to every single hypervisor because it's a stateful kind of solution, right? You have the state in every single hypervisor because you run your OpenVSwitch either on the kernel or as a VM, OVA, whatever.
You're speaking of a specific use case? Or?
Yeah, I'm gonna get there.
Okay.
How can you scale the solution, specifically when I talk beyond Metro, if you have to push a state to every single hypervisor?
So the question is, if you have a lot of hypervisors, how can you afford to push the state to all of them, a centralized controller?
Yeah, especially beyond Metro networks, right?
Yeah, I don't work on our controllers. I know that we use a cluster of multiple controllers, but we've managed to scale to thousands and thousands of hypervisors. So it's not been easy, but it seems to work. So I don't know how.
So if we do this OpenVSwitch again, I mean, given that now we are 2013, how would you have done it?
Oh, I think I redo it about once a year. Good question. I think that the approach that's come up of sending every pack to user space would just open up so much flexibility that we'd be able to re-architect everything, refactor everything however we want, once a quarter if we decided to. And I think that's the approach that I take these days, and we're likely going to go that direction. And we haven't figured it out yet. We're still designing, but it's looking very exciting. Do you have any more specific questions?
Like, for example, I mean, you had to do a lot of hacking in the printers and that kind of stuff initially in order to get the sensor working when you did not have the source and that kind of stuff. Now that you have some source and for the hypervisors and that kind of stuff,
So the question is, given how the industry has changed and how the hypervisors now tend to be open source, what can we do differently? We've done our best to integrate where necessary, but I don't think you want very tight integration because you just want some sort of interface in the middle that you can agree on. And so far it seems like OpenFlow is that interface. There are many ways I'd change OpenFlow if I could, but that's mostly a political problem and not a technical one, and I don't excel at political problems.
NetMap paper presented some performance figures. In Nicira, did you do any performance?
So we had an intern. The question is, there was a paper about NetMap. It had performance figures, and did we look at it? We had an intern go through that last summer, and we basically concluded that the figures in that paper were presented in a way that made them look more impressive than they really were in practice. Also, the NetMap work, it left out a lot of stuff that you'd actually need to do to make vSwitch useful that would decrease the performance. So if you look at the sorts of things that we tend to do in hypervisors, we tend to set up things like tunnels. That needs to go through the IP stack because it goes over IP. If you a big portion of the NetMap gain is that you're not going through the IP stack. So that's going to be a huge challenge for us also. Now that this is a clear direction for us, it wasn't clear at the time that we couldn't get the performance we wanted with the architecture we have. It's becoming more and more clear. So at the time, it didn't seem worth pursuing that, and now our architecture is reaching its limits on the sorts of very, very difficult flow situations, and we're going to have to change the architecture to meet those. Did I answer your question?
Partially, you did talk about what performance data you're getting today.
With NetMap?
Yeah, no, without NetMap, with your implementation.
Can you?
With your implementation, what's the performance you're getting today?
What's your traffic look like? What's your hardware? It's not a single figure.
Yeah, let's say high-powered x86, so 4 cores.
Oh, okay. We only really care about performance on hypervisors. What are your VMs doing? I mean, it's not a single figure like a hardware switch where you've got 4 10-gig ports and you know that your ASIC can support 40 gigs of traffic. It's very dependent on what you're actually doing. If on your 4-core server, if you've got if your VMs are doing I don't know, large bulk downloads, then yeah, we can fill up your links at least one 10-gig NIC, probably more than that. If you're serving DNS and getting hit by 200,000 individual UDP packets a second, that's more challenging.
You mentioned ESX and Hyper-V in your slide. Any timelines or any when that might happen?
ESX, I believe that'll be this year sometime. Hyper-V, I don't know.
Any acceptance from Microsoft to consider this?
I'm sorry?
Is there any acceptance from Microsoft to put, do work for this?
We've talked to Microsoft before, but Microsoft is actually fairly open in some ways. In this respect, they've got a very open API for their switch, and I think that you can just, if you've got the right access to MSDN, I think you can just get their DDK and and build something. And in fact, we had a very confusing phone call with Microsoft a couple of years ago. We'd talked to the Hyper-V group there and said we were interested in adding support, and introduced ourselves as Nicira, and we found ourselves on this phone call with them, and they gave us this total brain dump on how everything in the Hyper-V networking stack worked, and telling us all these dates about when stuff would be available and when they were announcing and what you'd have to do, and we were just flabbergasted. We were like, wow, these guys are so open. And then an hour after the call, they emailed us and said, oh, we thought you were Microsoft employees. please don't share any of that stuff. We'd introduced ourselves properly. Yes, please.
Yeah, so a quick question, how to understand what's the internal relationship of like OpenStack versus Open vSwitch? Is that fair to say like OpenStack is just one kind of sort of northbound API to the user interface?
That's the technical relationship. The question is, what's the relationship between Open vSwitch and OpenStack? Quantum, I assume, is what you mean. So the answer the answer is yes. Quantum is sort of one northbound API for Open vSwitch. It's a little complicated by the fact that Nicira and now VMware more or less drives the Quantum project, but it doesn't have any secret APIs. It just uses the normal ones that any controller would. Yes?
So the current OpenFlow specification seems to struggle a bit with having support for commercially available silicon. And some of the very nice proprietary extensions you showed here today is clearly outside of that. So it's really hard to put that back. Or are you figuring out a way to get hardware vendors to actually implement the very nice stuff that you're showing here in hardware, so we can get hardware back Open vSwitch features like the ones you're showing, which, and again, is very, very useful.
So the question is, these advanced features, are you going to figure out a way to get them in hardware switches? And we've tried. We've launched any number of internal projects to work with hardware switches. Every one of them has failed. Either we're just not very good at it, or it's just not a good model for what we're trying to do. Now, one point to mention there is that we weren't trying to build general purpose OpenFlow implementations. We were trying to build OpenFlow implementations that could support the kind of controllers that we're selling to our customers, and those requirements are different than what you need from a general purpose OpenFlow implementation. So. My guess is that a general purpose resubmit would never show up in hardware because hardware, my understanding is that they often simply can't afford to look in their DCAMs twice or 3 times, or the 30 times that MVP would like to, or anything like that.
Which makes Mac learning impossible with OpenFlow and hardware.
It makes it impossible to do it through this approach. In general, I think that hardware is often designed for a special purpose. I mean, that's what the AS in ASIC means. And so if you try to use it in a general purpose fashion, well, you'll often be disappointed. Yes?
If you're building OpenStack also with Quantum, what version of OBS does it come with? Does it come with the upstream one, integrated kernel, or?
I have never worked on OpenStack for Quantum. I don't know what the answer is. Yes?
Yeah, I was surprised. I talked with a few rack-spec engineers like a while back. They told me they are very happy about the Nicira, what Nicira has did for them with Cisco. So I would thought Nicira already worked with Cisco to twist some of their hardware for rack space. I was wrong there?
I don't know anything about Cisco Rackspace Nicira collaboration. I know that Rackspace is generally happy.
Yeah, obviously they speak very high of people.
Well, thanks. We work very hard to keep them happy.
And but I'm just curious, when you guys got acquired, how many people you have?
I think there were about 70 engineers and probably 30 other staff when we were acquired.
Does OBS plan to support NVGRE's IP encapsulation?
Question is, will OBS support NVGRE? My understanding is that NVGRE is not that different from GRE. It's more like a control plane on top of GRE. If you look at like the VXLAN control plane, for example, and I don't know the NVGRE one, but if you look at the VXLAN one, then that's something that you can actually layer on top of the encapsulation. And our experience is that a lot of people aren't even actually looking for the control plane because it requires IP multicast to be implemented and working in your environment, and a lot of people don't or can't or for some reason won't implement IP multicast. I don't know enough about NVGRE to see if, to say whether the situation's different there.
What kind of challenges do you face in terms of getting OBS working on Amazon? Easy.
I guess I don't know any. I don't know of any. I think the main challenge with getting OBS on Amazon would be to get Amazon interested in OBS on Amazon. I think they actually do routing instead of switching, but I don't know much about EC2.
No, like for example, if I have my own VPC, I want to put a OBS instance there so that I can network within my so-called subnet.
I haven't thought about it. Presumably OBS would run on EC2. I don't know.
EC2 you will get only one interface, but if you go with the virtual private cloud, then you can have multiple interfaces.
Okay, I don't know enough.
8 o'clock, so I think it's time to wrap it up. Thank you so much, Ben.